Large language models have moved beyond simple synthesis to the active generation of testable, novel scientific hypotheses. Many researchers treat these systems as deterministic knowledge repositories, expecting the model to retrieve absolute facts like a traditional database. Their actual architecture is stochastic. Instead of retrieving facts, they are token predictors that operate purely on the probabilistic generation of word chains. When this stochastic process is applied at scale, the system eventually generates hallucinated, mathematically invalid data. This creates a systemic risk in academia. Relying on cognitive offloading compromises the researcher's mastery over the material and introduces corrupted information into the literature. Utilizing AI for rigorous discovery requires offsetting these inherent hallucinations through highly constrained structural architectures. We manage this stochastic risk by mapping AI integration across 3 distinct ascending levels of autonomy. The baseline of human discovery follows 5 traditional stages: observation, hypothesis, experiment, analysis, and conclusion. AI systems are now overtaking this entire loop in 3 specific evolutionary phases, moving from a simple tool to an analyst and finally a scientist. As the system moves up this taxonomy, human intervention decreases, which increases the necessity for strict architectural oversight. Mastering this framework allows researchers to transition an LLM from a summarizer into an autonomous engine of discovery. Level 1 autonomy is defined by explicit task automation, where the system operates strictly under human direction. Researchers use specialized systems like LitLLM to execute semantic literature retrieval across massive academic databases. These models can also parse thousands of abstracts to automatically reformat disparate findings into structured tabular data. The ethical framework serves as the mandatory protocol here, requiring researchers to define specific constraints and verify every output against primary literature. Prompts that lack a detailed methodological background will consistently produce outputs with diminished reliability. While Level 1 accelerates cognitive labor, the human researcher retains all responsibility for the validity of the results. At Level 2, the model functions as an analyst, processing complex multivariate relations and identifying high-level data patterns. The researcher defines the overarching problem, and the AI independently identifies conflicting methodologies within the research field. This enables literature-based discovery, a method used to mine undiscovered public knowledge hidden within the archives. The system maps connections between disparate facts that usually remain isolated by disciplinary silos. Standard prompting fails at this scale. Grounding the data requires the integration of structured scientific knowledge graphs. We utilize the KGCOI framework, a knowledge-grounded chain of ideas, to force the model to verify its reasoning against established scientific nodes. The graph structure enforces strict causal boundaries, preventing the model from suggesting associations that are biologically or physically impossible. By anchoring stochastic predictors to these rigid graphs, we convert a text generator into a reliable analytical agent. Level 3 introduces an exploratory agent capable of autonomously coordinating the hypothesis generation and analytical refinement stages of the loop. This requires a shift from single prompt generation to complex multi-agent frameworks. We arrange the model into specific personas: scientist, analyst, and critic. They engage in an internal dialogue to collaboratively generate and iteratively refine a central hypothesis. The system then applies a Monte Carlo tree search to rigorously test statistical viability before presenting claims. The critic agent is specifically prompted to simulate harsh peer review conditions, finding methodological weaknesses without human intervention. Ultimately, Level 3 functions as a high-speed simulation of the entire academic peer review pipeline, fully executed in silicon. The bottleneck of high autonomy is evaluation. We must determine if the machine has produced a genuine insight or a sophisticated paraphrase. Traditional evaluations fall short because they cannot capture the underlying scientific merit of an idea. Automated metrics map the hypothesis into a high-dimensional space to measure its distance from all known literature. This mathematical calculation of semantic distance allows us to assign the output an objective novelty score. However, automated scores cannot assess real-world feasibility. That requires human expert intervention. We use double-blind pairwise comparisons to pit AI theories against human models, stripping away bias to find the most viable research path. The value of an AI scientist relies on our ability to aggressively falsify its outputs, using both algorithms and human experts. As discovery accelerates, the researcher's objective moves from manual hypothesis generation to the architectural direction of agentic workflows. The human researcher now defines high-level analytical goals and constraints, while the autonomous loop executes the data compilation. The next frontier involves translating these digital hypotheses into physical reality. We are rapidly moving towards robotic automation, where models write direct execution scripts for automated wet lab environments. Online reinforcement learning then allows these systems to assimilate experimental results and adapt their research strategies in real time. One ethical boundary remains absolute. An artificial intelligence cannot hold academic authorship. Authorship requires the capacity to assume ethical liability, a responsibility a stochastic token predictor cannot possess. Autonomous systems will drive the speed of discovery, but the human mind remains the sole arbiter of truth, accountable for the epistemic rigor of the science.